We are privileged to have seasoned industry experts today with us that will share their knowledge, insights, and on thermal management workflows for real-time applications, methodologies, tools, and best practices. We will have a dedicated Q&A session at the end, so please feel free to drop your questions in the chat dedicated for Q&A. We will make sure to answer all your questions either today at the end of the session or offline. We're going to send individualized answers to all your questions. So without further ado, let's start. A great welcome to Daniel Stepansky from SEG Automotive. Daniel comes with a robust background in electrical engineering, particularly in control of electrical machines. Having previously worked for Bosch, Daniel has been an integral part of SEG Automotive for several years. He specializes in application software development for 48-volt hybrid electrical machines. Over the past 2 years, Daniel has been a driving force in high voltage electrification within SEG, serving as a technical software expert and software project leader for high voltage electrical drives. So thank you very much, Daniel, for joining. Over to Metasystem. Today, there are Antonella Finamore and Gabriele Gangale. Gabriele is at the forefront of computational fluid dynamics, simulation, and thermal management for onboard chargers at Metasystem as a key liaison between the mechanics and the hardware departments. Gabriele ensures a balance between feasibility and thermal management of final products, and his work is critical in meeting the increasingly stringent requirements that we all know by car manufacturers, making him an essential figure in Metasystem innovation. Antonella, on the other side, Finamore brings her expertise from the hardware department, where she focuses on the analysis and design of power architecture and control strategies. Her work is pivotal in understanding the thermal behavior of power devices. By creating simulation models of the entire onboard charger, Antonella provides essential data for the mechanical departments to optimize the thermal performance of their products. So her contributions are vital to the advancement of thermal management technologies within Metasystem. So nice to have you here, both of you. Thank you for joining. On to Nikolai Gorte from Infineon. He has been a dedicated application engineer in Infineon for over 5 years. He specializes in supporting the G2 products of the hybrid pack drive module, SiC module. Nikolai's extensive experience in the automotive industry, including his work. He worked for OEMs like Volkswagen. It keeps him with a unique insight into the automotive applications and innovations. His contributions are for sure instrumental in advancing hybrid and electric drive technologies. So welcome to you, Nikolai, and thank you for joining also to the whole Infineon here. Francesco Toso, last speaker of today, is coming from Newtwen. He's the CEO of Newtwen and co-founder. He graduated in electrical engineering from Padua and completed his PhD in industrial engineering with a focus on electrical drives and model predictive control applied exactly to power electronics. Under his leadership, Newtwen has been at the forefront of real-time monitoring software solution for sustainable growth and technological innovation. Very excited to have you here. Thank you for joining, also for the people that were joining just now. We are very excited to hear from these industry leaders today and learn about cutting-edge technologies and strategies that they are developing in their own work. So let's give a warm welcome to all of them, and let's keep this as inspiring and informative as we can. So let's start to hear this perspective on the topic. The agenda of today is going to bring them one after the other, telling us how they are working internally, what methodologies, what struggles, what challenges, what actually can be done at the team level, at the organizational level, at the individual level, and what maybe you can take some inspiration from, you can replicate what works and bring this portion of the industry at new heights. So thank you very much. I would like now to leave the floor to Daniel, our first, I would say, event speaker for today. Daniel, the floor is yours. The only thing that I would like to ask to everyone, to the speaker as well, please try to be in the time allocated so we can all have a nice Q&A session at the end. Thank you very much. Welcome, Daniel. The floor is yours.
Thanks a lot, Giuseppe, for the very kind introduction. I hope you can all see my screen and hear me very clearly.
Yes, we can, Daniel, okay. Indeed.
Thanks. Then welcome everybody to a very short introduction of thermal management at SEG. Before jumping right into the topic, I would also like to use this chance to shortly introduce SEG, who we are and what we do, in order to give you a short overview about the available expertise in SEG. So SEG, formerly coming from the Robert Bosch company, now being independent, has a long history, roughly 100 years of background in the development of electrical machines, especially for starter motors and alternators. In the past years, we were also moving more and more into the electrification business, starting with our mild hybrid system, the so-called boost recuperation system, or in short BRM, and also high voltage development, where we are focusing on selling high voltage inverters, traction e-motors, relays, and also complete e-drive systems, either integrated motor inverter solutions or also complete e-axle. In all these applications, we are focusing on commercial vehicles as well as passenger cars. Additionally, we are active in the rising market of light electric vehicles, where we offer several products for electrification, like mid-mount motors, hub motors, with the related controllers and virtual control units, and even also e-bike motors. So as you can see, our passion is certainly the e-machine and inverter world, and that's also why I will focus on this in today's presentation. Speaking about thermal management, let's firstly have a look on the different products I just showed and the different thermal requirements and protection for or cooling measures. Starting from the bottom with the 12-volt machines for ICE, which is mainly our starter motors and generators, here we see that these products are very close to the combustion engine as the main heat source. Due to simplicity of the components having no active control, the thermal protection in this case would be mainly handled by the design by guaranteeing that the hotspot of the machine will not exceed the maximum allowed temperature under worst case conditions. Then let's have a look on our mild hybrid machines, which are used typically in P0 topology. That means the electrical machine is connected to the combustion engine via the belt. Also here, this machine is very close to the combustion engine and within the motor compartment. That means high ambient temperatures ranging up to 120 degrees or even sometimes 150 degrees for up to 60 minutes, which is a lot of thermal stress for these components. The machines are often air-cooled, but due to this ambient temperature, that doesn't really mean that it's, let's say, really cooled. Sometimes it's even heated by this ambient temperature. So here the thermal protection needs to be considered on one hand in the design level by selecting higher graded temperature components, especially for the electronics that can then withstand this ambient temperature, and on the other hand also by actively reducing the output power of the components. For traction drives, the main heat is coming from its own losses. So here in the inverter and machine, the losses are directly happening, and therefore we focus on mainly on active protection. That means reducing the output power of the e-drive and then therefore protecting the machine. For enabling maximum power density, of course, here we need good thermal modeling techniques and optimized cooling concepts that allow higher continuous power. So typically here we see oil or water cooling as the main cooling medium. In light electric vehicle applications, there is also air cool as one typical application. In traction drives, the heat is not always the undesirable. So we also see here that there are some conditions where heat is desirable. For example, starting in cold conditions, cold ambient temperature in winter, there, especially for the battery, that could be a scenario which is not that good. So here the battery needs to be warmed, and thermal management for e-drives can also mean in this case that the electrical machine need to be able to create additional losses in order to heat up this cooling system, which is then finally heating up the battery. Now looking at the operation conditions of an e-drive, let me shortly explain the typical limiting components. Here we see basically in this diagram the speed and torque diagram of an electric machine. The red part of the graph indicates the thermal critical operation region. Here the losses in the system exceed the amount of heat that can be removed by the cooling system, and therefore this operation is only possible for a short amount of time. The target finally of the thermal derating functionality is to bring the system into the safe operation area, which is shown in gray, before basically the temperature exceeds the maximum value. So the target finally for the steady state condition would be exactly the boundary between gray and red operation area, where the heat generated by the losses would match the heat which is transferred out of the system by the cooling system, resulting in a stable temperature. And this is then the maximum safe continuous output of the eDrive system. And exactly for this, we need very accurate measurements or temperature estimation methods of the machine, because estimating the temperatures too high would basically mean reducing the maximum continuous output power, whereas estimating the temperature too low eventually means destruction of the machine. Additionally, depending on the operation region, like high or low speed operation, we see different components might be relevant for thermal derating. So in low speed area, thermally critical component is usually the power switches in the inverter. For higher speed in the field weakening area, we see that typically the stator windings or the rotor magnets are relevant for thermal derating. However, these components relevant for the derating are highly dependent on the design. So for example, for air-cooled machines, the rotor might be the hottest at medium speeds due to the thermal losses being higher at this speed compared to heat transfer out of the system by the cooling air, which is again dependent on the rotation speed. With water-cooled machines, it might be that at this medium speed, more the rotor stator would be the critical components. So that means finally, in order to see what is the critical component in which operation, a good system knowledge is crucial to maximize the utilization of the eDrive. I was also asked to provide some short overview of our best practice for thermal management. So here's what we learned is very important for being able to do good thermal measurement. The first is thermal measurement is starting with a good design. And good design in this case means close collaboration between the different development areas like system, software, and hardware development. One crucial topic for thermal optimization is, for example, the efficiency. Creating less losses means less heat, which is obvious, but on the other hand, optimizing the single components doesn't necessarily mean the complete system is optimized. One good example would be the PWM frequency. Some portion of the inverter losses are coming from switching losses. To reduce switching losses, the PWM frequency would need to be decreased, which is then directly proportionate to these losses. But at the same time, lower switching frequency means higher current ripple in the e-machine, and this is again increasing the electromagnetic losses. So here we see both systems need to be evaluated, and a typical solution would look like to adapt the switching frequency based on the speed, where inverter would be more critical at low speed and e-machine at higher speed. Another important point is optimized cooling concepts. That means at one hand to analyze how we can transfer more heat out of the system, and also to identify critical components and optimize the placement in a way that hotspots which are much hotter than other temperatures are avoided. So another important question is here where to place the sensor in order to derive a good relationship between the sensor value and the relevant component. And the third point is an optimized derating strategy. So that means how do we handle situations where the maximum temperature is being reached? So here, good real-time monitoring is needed to go as close as possible to the boundary conditions. Therefore, the thermal model that captures the temperature must be as precise as possible. Another factor is to implement smart ideas to maintain the output power as long as possible. For example, I just spoke about the PWM frequency. So that means instead of reducing the output power of the system, of course, we can also think about if there might be other components that might be able to handle a little bit more losses, and then online optimize the system by shifting losses generation from one component to another, for example, changing PWM frequency. It can be PWM frequency, it can be modulation techniques, could be the excitation current in case of a separately excited machine. So there are plenty of options, and basically to see all these options, there we need a very close collaboration of the different design teams, and that is why an integrated system solution will always have some advantages against buying single components. And then finally, let's have a look at the way how our thermal simulation and modeling workflow looks like. So starting with the design phase, where we utilize detailed 2D or 3D finite element methods to derive electromagnetic behavior, which we use for loss calculations, for example, iron and magnet losses, but also do simulations and finite element methods for fluid dynamics to understand the thermal behavior of the electric system. In order to then identify hotspot and potential positions for sensors. Speaking about the inverter, there we also identify switching and conduction losses of the power switches using the characteristics from the datasheet, supported by electrical simulations and thermal analysis to understand the thermal path and determine thermal resistance between the junction temperature and finally the cooling medium. Of course, simulations are always subject to inaccuracy. That is why the simulations are also frequently validated by real test bench measurements or by doing fundamental analysis via experiments, for example, to analyze the heat transfer between different solid materials. This gives us a good fundamental understanding of our system. In addition to that, for real-time monitoring, there we need to consider also other factors like limited calculation power in the embedded microcontroller, but also external factors like product cost and reliability. For example, of course, it sounds easy to just place sensors everywhere, but that is often no solution. On one hand, due to the cost, but also since it's sometimes difficult to realize a sensor at the required position, for example, on the rotating rotor of the machine, where the magnet temperature would be especially relevant, but it's very difficult to place a sensor. Or even in the stator windings, a sensor is not that optimal because here we have a cable between the inverter and the e-machine. There's vibration during the operation, so it's not that easy to have a sensor reliably placed somewhere in the stator of the machine. Due to that reason, we need good thermal models that are precise and at the same time easy enough to be run on a microcontroller. Within SEG, therefore, we basically use two methods to do such kind of complexity reduction. One way we call the expert approach. So here, a dedicated expert defines the thermal network in a way that this network can reflect the behavior of the machine after applying some calibration methods with automated calibration routines, which is then fed by measurement data. The other way would be to do some this network definition via some kind of mathematical optimization, like, for example, also using the Newtwen fabrica. So here, of course, the challenge will always be to maintain some kind of physical relationship so that this calibration is still possible with real-world measurements. So finally, this information derived out of these systems can be used on one hand for thermal monitoring, but on the other hand also for system optimization. That means using the derived temperature in order to get more accurate algorithms, for example, in the torque estimation, where we can consider the temperature of the rotor for the dependency of the rotor flux on temperature. So that was a very short introduction into what we do in SEG and how we do thermal management. Thanks a lot for your attention.
Thank you, Daniel, so much. I think it was very interesting to hear a couple of things that are very rooted into your practices. So thank you so much. I would kindly ask now Gabriele and Antonella to join me on the stage.
Thank you, Giuseppe, for your introduction. And today, my colleague Gabriele and I speaking about our thermal management strategy. And our presentation is divided in two parts. The first part is dedicated to hardware team activities, and second one to the thermal team activities. And as you can see in this slide, between these two teams, there is a continuous collaboration. But next up, before talking about our strategy, let me briefly explain what is our product. OBC onboard charger is a power electronics device that converts AC power from external sources into DC power to charge the battery pack of electric vehicles. Our OBC is able to respect all charging standards as requested by the market. And moreover, due to in the recent years, OBC plays a crucial role in bidirectional charge. Our OBC supports all vehicle 2X functionalities too. For this reason, it is clear to develop an efficient thermal management becomes mandatory. So for this reason, we construct a thermal strategy based on the evaluation of conduction losses and preliminary conduction losses and switching losses. Our strategy is based on the information given by manufacturer of power devices. In these slides, you can see an example of datasheet of power MOSFET. Using this information, we construct an XML files that contain the electrical filters of our device and the thermal network, both core or Foster. The choice depends on the information given from the manufacturer. After that, we construct a thermal model in our simulation tool, Flex, that contains both turn-on and turn-off characteristics losses and conduction losses too. The initial temperature is given by thermal team, and after Gabriele explain us how they choose this value. And after that, we use the thermal model that we construct in the full power stage that in these slides, you can see an example of first power stage and its control. For each device, we are able to estimate the junction temperature. In this case, you see a MOSFET, junction temperature, conduction losses, and switching losses. These figures are calculated for all power devices and for all power stages that compares in our OBC. These values are very important and necessary for mechanical team in order to investigate the overall thermal behavior of our OBC. And for this reason, I now leave the floor to Gabriele.
Okay. Now, when we received from the power electronics team, the hardware team, all the power losses of each component, we can manage the overall behavior of the overall thermal behavior and we are using the CFD to do this. And the first thing that we typically do is to conceive an efficient cooling channel that can be capable to fulfill all the customer requirements. In particular, the first of that we have to fulfill is a pressure drop customer requirement, and it is all these conditions that we have to fulfill are typically in contrast one to the other, because as lower is the pressure drop, the maximum pressure drop, the worse will be the thermal exchange and the heating exchange. In this case, we can see an example of one of these cooling channel, and where there is highlighted the superposition between the cooling chamber itself and the heating components, that in particular in this case are the topside cooled MOSFET. And there are other constraints that we have to fulfill. In particular, we need to have the highest speeds of the liquid. Just besides or under the heating components, we have to fulfill issues about structural strength of the overall system. So we have to consider fixation points and welding lines that will modify the final aspect of the cooling channel, and also feasibility in terms of die cast or friction stir welding are constraints that will modify the final shape of our cooling channel, that at the end will not be as optimal as we would like. After that, we do a thermal simulation, always by means of numerical models. And also in this case, we have to consider the worst case condition, and looking at the customer requirements, we have to find the right combination to assess which is that critical operating point. In this case, of course, it will be the maximum temperature, inlet temperature of the coolant, the maximum environment temperature outside the OBC, the maximum power erogated by the system, and the minimum flow rate of the coolant. Once we have considered this critical operating point, we can explore all the many operating points that are inside this region of worst case. The objective of the thermal analysis, of course, is also to improve the performance of the cooling system if needed, where needed, and highlight some thermal issues if there are components that exceeds their maximum allowed temperature, and also verify the compliance with the customer requirements. What is interesting is how we found a way to simulate the MOSFETs that are the thermal bottleneck of the whole system, because they are the component that will experience the highest temperature in all the system. So we do not explicitly model this by numerical method, but we stop our simulation at the thermal interface material. Thermal interface material is another crucial element in our simulation and in our OBCs. Of course, the highest performance, for the higher performance of the thermal interface material, the better is we are capable to have heat rejection from the component to the cooling channel. But also we have to to be aware of the cost, and to be aware of other issues like mechanical tolerances and electrical conduction. So our numerical analysis stops at the surface where the MOSFET is in contact with the thermal interface material. We retrieve by the simulation the temperature on this surface, and then we retrieve the junction temperature by means of the simple relation that you see in the bottom of the screen. So we add to that temperature the power losses times the thermal resistance of the component that is provided by the technical datasheet. In this way, we can forecast in advance which will be the critical points in where we expect the rating. Why we expect the rating? Because we are exceeding the maximum temperature allowed by the MOSFET components. In particular, if the MOSFET components have a maximum power for the junction that is typically of 175 degrees, we keep a margin of about 25 degrees. So our maximum temperature would be 150. So these are the regions of the operating points where we expect to be in the rating mode. The rating mode is, of course, a reduction of the total power that can go out from our system. Now it's time for the firmware and hardware team to collaborate in a loop, and once we have a good thermal model of the system, and we can validate it with an extended measurement campaign in which we put a lot of sensor inside our OBCs, we can forecast the temperature of the most critical components related to the temperature that we can read all around our devices. At the end, we can put some NTC sensors that are in specific position inside our system, inside our OBC. Typically, they are on the printed circuit boards, and we can correlate the values of these NTC sensors with the state of the overall thermal state of our OBC, and then we can write down an algorithm that put in relation the evolution of the NTC sensors with respect to time, so we know how fast they are rising up. For example, T1, T2, and T3. This is just an example, but typically they are no more than 3 or 4 NTC sensor all around our system. We also use the power out, and the voltage. That is another crucial element of our algorithm, and then we can forecast if we are or not in a state of over temperature of some of other components. If the answer is yes, the system will decrease the power out, and then we are going to read in loop our variables. If the answer is no, if we are already at full power, there is no reason to increase power instead of maintain the same status. So that's it. A very quick glimpse to the challenges that we daily face about the thermal management in Metasystem. But I am confident that many of the concepts that were exposed here are the same as our colleague in SAGE. I'm happy to have the same problems.
Thank you. Thank you so much. Very interesting. Thank you very much both again. I will now ask Nikolai from Infineon to join us, so we can also have an additional view from a semiconductor producer that can also spark and shed new light on how they see the same or the common elements that we were discussing.
So today I would like to introduce to you which methods are available to estimate the chip temperature or the power modules. So here you can see the content. I would start with simulation method. The next I will present the correlation method. Then the method which with the thermocouples, and lastly the IR thermography method, and finally I present the conclusion. So here you can see the simulation method and the correlation method. The application of the models also depend on if the data of the power module available or if the real power module is available. If the power module not available, then simulation model is used first. No? So a simulation method is based only on the theoretical values. It's also very complex. And this method is used now to roughly estimate it of the chip temperature in the development phase of the project. As a result, there may be a discrepancy between the simulation and measurement results. And second one, this is the correlation mode. With the correlation mode, the value of the temperature will be correlated with the chip temperature. Each model has an NTC or temperature sensor, and what we do, we correlate the junction temperature on the chips with the NTC. So the temperature sensor and the power module need time to reach the steady state temperature. Therefore, it takes time before we install the state. Therefore, we need more than 1 second for this. So otherwise, the correlation would not. We need to wait more than 1 second in steady state. Otherwise, the correlation would be not correct. In addition, it must be considered that the short temperature on the sensor is not the same like chip temperature. For this reason, we create like a lookup table. And this lookup table shows the chip temperature as a function of the NTC temperature. So next one, I will present the thermocouple method and IR thermography method. The thermocouple method is used to validate the thermal inverter simulation. In this case, it is also important that the power module and the thermocouples are in the steady state. Otherwise, the measurement results will not correspond to the true chip temperature. This method is often used for the development of derating function, but this method cannot be used for every chip. Maybe we have chip sites and so on. We have big chips, you can use it because you put the thermocouple directly on the chip. If you have small chips, it's very difficult to use it. The second method is the AI tomography method. The AI tomography method is also used to validate on thermal inverter simulation. To apply this method, correlation must be first made between the junction temperature, electrical junction temperature, and junction temperature from the AI camera. And this method provides an overall overview of the thermal behavior of the whole model. Maybe we can see not only one point of the chip, we see the whole model. We see the thermal behavior between low side, high side, between the chips, between the bond wires, and we can see the temperature of the DCB. This is also very important. Compared to the other method, it's also possible to measure the transient behavior of the chip temperature, depending on the characteristic of the camera. Maybe it's also depend on the frame of the camera frame rate or resolution. In this slide, you can see the methods, application of the methods and the conclusion. The slides methods are sorted by accuracy. The simulation method can be generated relatively quickly, but large deviation can arise between the simulation to reality measurement results. So the correlation method, this temperature sensor method, represents the chip temperature well, but in certain operation point. So the thermocouple method directly represents the chip temperature in steady state, can be used depending on the chip size and provide selected temperature, because we measured only the one point of the chip, and this point can represent the junction temperature, can also not represent the junction temperature, depends on the position. The best representation of the chip temperature is provided by AI tomography. It is contactless and provides a thermal overview of the whole power model. So what about the application of the methods? Most methods are mainly used in steady state. Uncertainties may arise when using the methods. Therefore, safety margin are used. We already have seen. In some cases, customer use up to 25 degrees as a safety margin. So on the right side, you can see the diagram, and here you can see orange dash line, green and gray dash line. The orange dash line represents the maximum junction temperature. In this case, is our power module defined up to 200 degrees. Typical operation point is 175. Yeah, and the model is defined for 175. So considering the safety margin, the power module is only used up to 150 degrees. This means that the power module is the power module's full potential is not used and performance is waste. In this case, more than 10%. This year, we based more than roughly 10% performance. So, and then most methods appeared in a safety state or steady state. Now we come to the conclusion. Most methods appeared in steady state. Dynamic process cannot reproduce, and in addition, the full potential of the power module is not used. So, thanks for your attention.
Thank you, Nikolai. I also see some questions for you in the Q&A. We're going to answer them at the end. I would like to keep the time straight. So thank you very much, Nikolai, for giving your overview of this. I would like to bring on screen Francesco Toso from Newtwen, that is going to give us an additional overview and give us an additional understanding on what can be done on these topics as well. So please, Francesco, the floor again is yours.
Well, thank you very much, Giuseppe, for the introduction. Well, I would like to start giving you a simple definition of what is a virtual thermal sensor. So virtual thermal sensor, or VTS, at the end is a software solution that can accurately estimate the granular thermal behavior of a component in real time across all its operating conditions and lifetime. This kind of technology has two main advantages. First, they can measure where real sensors can't, and second, they can predict future thermal scenarios within predefined time horizons. These are the two main functionalities that are needed if you want to build an optimal thermal management control of your, let's say, system. So let's see which are today the main concerns among virtual thermal sensing technology, and in particular, which are the automotive KPI requirements. So let's start with the accuracy. VTS temperature estimation must be quite really accurate. So the temperature must be estimated within an error range of 5 Celsius degree under varying operating condition. What does it mean? Let's take the electrical machine as an example. If you want to estimate the rotor magnet of an electrical machine, we need to design a model that has to be accurate enough during all the wide range of operating condition of this machine, which means that if I change the coolant flow rate, for example, or if I change the inlet temperature of the coolant, the phase current, the rotor speed, the model must be still accurate inside that range. So it's really high. It's really a hard challenge, let's say, but it's not the only one, because also real-time feasibility is also tough. Let's consider a standard automotive grade controller unit. In this case, VTS execution time must be less than the 2.5% of the task period where it is implemented. What does it mean? For instance, for power converters application, we have already seen with, let's say, high fast dynamics, VTS are usually executed within the task period of 10 milliseconds if you want to observe these really fast transients of the temperature, right? And which means that the execution time must be less than 250 microseconds. So let's stop one second here. And the challenge here is really high. We need to obtain a model, a unique one, that needs to be implemented in real time within microcontroller units that usually they have, let's say, low memory and computational power within this fast period task of the microcontroller. And this unique model must be really, really accurate within all the wide range of operating conditions that this device will face in production. So continuing with which are the other constraints, also memory footprint, of course, plays a quite strict requirement. It is influenced by manufacturer. For instance, here we have a customer reference case where in this case, the memory footprint constraints was to implement a model with less than 2 kilobytes of RAM and less than 100 kilobytes of flash for the implementation in real time. So let's say that once you can satisfy the automotive requirements, you can finally achieve the production implementation of this virtual thermal sensing technology. So let's see which is the added value. Here there are the most wanted virtual thermal sensors in the, let's say, automotive market for ePowertrain components. Some of them has already been mentioned. So starting with the electrical machines, safety and performance are really tied with the temperature, for example, in the film insulation of the head windings, in the magnets inside the rotor, in the bearings in the shaft. But unfortunately, all these quantities are not measurable, or sometimes it's even impractical. Let's consider, for example, the rotating part. For power converters, as already been mentioned a couple of times, that junction temperature is the critical bottleneck. And it's impossible to be measured in production for, let's say, engineering constraints, but it is the state variable directly connected with the efficiency, with the performance, and the safety of this component. Other, let's say, key variables are stated here. For example, also coolant flow rate is quite interesting to have as information for controlling the cooling system. Unfortunately, here we have, for example, cost constraints. Flow meters are quite expensive, and to scale this in production for millions of pieces, of course, is not allowed. And another important point and topic that Nikolai has just mentioned here. Here we are talking about devices with high current density, which means that in few distance we have a huge gradient of temperature, which means that one point of measurement is really not enough. If you want to have the best-in-class thermal management control, you also need to have granular thermal management, thermal behavior insights in real time within your controller unit. Unfortunately, All these quantities stated here are not measurable with hardware sensors, and companies today are really struggling in trying to estimate them in real time, satisfying the just stated automotive requirements. And that's the main reason why today control are using oversized safety margins, which can compromise the efficiency and also the profitability of these components. With VTS technology, this can really change because you can have these granular thermal insights in real time within your controller unit, and you can exploit it in closed loop control. Here we can see an inverter case example where, for example, VTS on the maximum junction temperature of semiconductor surface die of power modules is running in real time. So it's providing to the control this information in closed loop. And for example, controller number 1, what it's doing is derating first the switching frequency, which is one of the main, let's say, cause of losses, so heat sources in the system. And this derating, of course, until a certain lower bound limit, will, let's say, allow you to increase the maximum continuous time where you can hold the peak current, but controlling the junction temperature within its safety limit. So once the controller number 1 achieved its lower bound limit, controller number 2 will start modulating the current in a dynamic and continuous way, such that, of course, you can control the junction temperature within the safety limit that now can achieve its maximum functional burden. That, for example, for silicon carbide, it is 175 Celsius degree. So this is directly translated into a couple of values. The first, increasing the time range where I can apply the peak current directly impacted the acceleration performance of the value of the vehicle, which is quite important KPI for automotive. And the second one is increasing the nominal current because I'm able now to control in a reliable way the junction temperature, directly increase the value of the inverters, since today these are priced with the current capacity. This technology is really disruptive, but which are the main, let's say, the key element, technological element, which are the methodology to create them at scale? Well, Newtwen is a software company which is working at the forefront of this next generation sensing technology, and we have developed Twin Fabrica, which is a unified engineering software platform which incorporates all the technical elements and know-how to make virtual thermal sensor at scale. We usually to start with the model as design coming from the user. I'm talking about CAD geometric models, material properties, finite element analysis models, CFD simulations. Once they are inside Twin Fabrica, these high fidelity models can be compressed. You can obtain a reduced order model. And now this reduced order model can be calibrated against experimental data, always from the user. I'm talking about data coming, for example, from functional testing, from endurance testing, sometimes from in-field testing. So data that the customer, the user, always have at its disposal. So leveraging this data, finally, here you have the chance to transform your model as designed into a model as manufactured, which now just needs to be optimized into a source code, which finally is the VTS, which can face the hard constraints of the third-party platform where it has to be implemented. So this unified workflow includes different scientific fields and disciplines, from multi-physics simulation to model order reduction, from control theory and artificial intelligence to firmware engineering. And everything is orchestrated with the aim to reduce the effort for companies to implement virtual thermal sensors at scale, satisfying the automotive requirements, increasing the value of their product, enhancing them with VTS technology. So thank you very much. I have concluded my presentation.
Thank you, Francesco. I think it was very interesting for the people out there. So thank you very much. I'm seeing your questions. Many are for Nikolai that I think answered already some in the threads. Nikolai, is there anything that you would like to specifically answer that you didn't have time on the chat?
Yeah, I have one question.
Yeah, please.
in terms of dynamic behavior, is thermocouple better than air? What's the best thermal resolution? This is a question. The best air resolution from air camera is less than 1%. It depends on the air camera. And thermocouple resolutions also depends on the thermocouples and the position of the thermocouple. If the position of the thermocouple is exact in the middle of the chip, then maybe you can get good results. But I already mentioned this is only one point. With air camera, you can see whole chip, and you can see voids, and you can see everything.
Thank you, Nikolai. Very interesting. We're going to collect the other questions, and if there is anything unanswered, we're gonna provide some dedicated answer. So thank you everyone for joining. Thank you the speakers for being here. As we come to the end of this event, I would like to extend a heartfelt thank you to all of you, especially the speakers for the valuable insights and also the active participation from the crowd. You were a lot of people out there here with us. I see also a question here for Francesco. So Francesco, do you want to spoil something on that question, the last minute one? It's for the VTS of the online temperature estimation. How can we get the initial temperatures?
It is possible. Here, it is, of course, one of the main features that VTS technology they have. They are quite agnostic to initial condition and boundary conditions, thanks to, in particular, between the three blocks that they were picturing in my last slide. Of course, I mentioned control theory, so VTS is always incorporating also state estimator, which is leveraging the, let's say, feedback from sensors and the model that at the end is describing the thermal behavior, also to estimate the right initial condition of the components, which is quite important, of course, for the resolution and the accuracy that is quite important as one of the main KPI for VTS.
Thank you, Francesco, for the answer. Right on time. Again, thank you everybody for joining. If you keep following our channels on LinkedIn and official channels of Newtwen, we are gonna try to organize more events like this as a time to reflect and share among the industry practitioners. So have a great day, afternoon, evening, morning ahead for all of you, and thank you for being here.